Hi, my name is Ben Berg, and my research presents a new methodology for scheduling parallelizable jobs. If we look at today's computing landscape, a wide variety of modern systems are purpose-built to exploit parallelism. And as a result, the kinds of applications we want to run on these systems are themselves increasingly parallel. This gives rise to the question of how to best run these workloads on these underlying systems. To address this question, my research asks how to allocate resources to parallelizable jobs, and in particular, how to allocate resources across a stream of many parallel jobs arriving to the system over time in order to reduce job response times, the amount of time that each job spends in the system. Now, prior work in this area can really be divided into theory and systems work, but my research spans these areas. In particular, I use a stochastic modeling approach. Then by analyzing our stochastic models, I'm able to derive provable performance guarantees. And finally, using our theoretical results, I perform systems implementation. So for example, I've implemented some of our theory ideas in databases, and here we can see the real-world impact of our theoretical results. So to see what this all looks like, let's consider a simple stochastic model of a multi-core server with 16 cores. This server will be tasked with processing jobs which will arrive to the system over time according to some stochastic process. Each job will have some amount of inherent work associated with it, which we can think of as drawn from some underlying distribution. So there will be some short jobs and some long jobs. And because these are parallelizable jobs, I can take an individual job like job 1 here and run it on all 16 of my cores. And the hope is that this job will receive some benefit from being parallelized. I'll describe this benefit via a job speedup function. So if I put cores on the x-axis here and speed up on the y-axis, I might hope that the job receives something like this green speedup function, which would tell me that the job runs twice as fast on 2 cores or 3 times as fast on 3 cores. But in practice, jobs tend to receive something that looks more like this blue speedup function, which is sublinear. Now note here that the job receives a diminishing marginal benefit from being allocated additional cores. Now, although this is a fairly simple stochastic model, it can still illustrate some very important questions in scheduling parallelizable jobs. For example, how should we maximize system efficiency? If we look at our speedup function from before, we can see that allocating all of our cores to any one individual job would be highly inefficient. We have a theorem that shows for any set of jobs how to calculate the efficiency maximizing set of allocations. And in general, these allocations involve limiting the number of cores allocated to any one individual job. This is a result from our Sigmetrics 2018 paper. One might also ask what to do if we have some jobs with less inherent work and some jobs with more inherent work in the system. Should we favor the short jobs or favor the long jobs? Well, it turns out that favoring the short jobs will tend to reduce response times. But if we allocate all of our cores to the shortest jobs, that will again be highly inefficient. So we actually have to balance a trade-off between favoring short jobs and maximizing system efficiency. We show how to optimally balance this trade-off in our Performance 2020 paper. Similarly, one might ask what to do when some jobs are more parallelizable than others. Do we want to favor those more parallelizable jobs? Perhaps counterintuitively, it turns out that we actually want to favor the less parallelizable jobs, keeping those more parallelizable jobs in the system to preserve system flexibility. Of course, if we favor those less parallelizable jobs too heavily, it will again be inefficient. So we have to balance another efficiency trade-off here. We show how to balance this trade-off in our SPA 2020 paper. Things get even more complex when we consider real-world systems, where we often have to balance all 3 of these questions simultaneously. Despite this complexity, I've had success implementing ideas from our theoretical work in real-world systems, such as an in-memory database, where we've shown that we can reduce mean response time by a factor of 2 using ideas from our Performance 2021 paper. So to summarize, my research spans both the theory and systems communities, and I've published at the top conferences in both areas. But my larger goal is to take this general research approach and apply it to a wider range of resource allocation problems. For example, I've also worked in resource allocation for caching systems, and going forward I'm interested in resource allocation for data-intensive jobs. Now these are jobs whose performance is determined by their ability to access the data that they need. So we can think of a server as having some external storage and some limited amount of DRAM. And as jobs arrive at the system over time, they'll pull the data they need from storage into DRAM. This means that we'll need an allocation policy to tell us which data to evict from DRAM to make room for arriving jobs. And this is complicated by the fact that newly arriving jobs might try to reuse the same data as past jobs. So this is actually something like a hybrid scheduling and caching problem. But beyond just CPU or DRAM, we can imagine jobs requiring all sorts of resources. So even longer term, my goal is to devise a general framework for tackling multidimensional resource allocation problems. Thank you, and please see my website or send me an email if you have any questions.